Hello everybody, and welcome to the beginning of chapter 13. We are looking at page 95 of the workbook here, and the topic of this chapter is going to be integral domains. An integral domain is a special type of a ring that has some particularly nice properties that we'd like rings to have. Okay, and to motivate this definition, I'd like to start with an example. Okay, so they introduce a term or a property called the so-called cancellation property in a ring. Okay, and here's what the cancellation property says. Okay, it says that if A is not equal to 0 and AB equals AC, then B equals C. Okay, that's a property that you probably use without even thinking about it when you're doing arithmetic in the real numbers. If you start with a statement like this, and A is not equal to 0, you can just divide both sides of the equation by A and get B equals C. Okay, but what's interesting is what the next sentence says here. Okay, so show by example that a general ring need not have the cancellation property. Okay, so I'm going to give you two examples of that. Okay, so let's start with the ring Z6. Okay, so addition and multiplication modulo 6 are our operations. And note that in that ring we have 3 times 2 equals 3 times 4 equals 0. Okay, do you see why that's true? Okay, because 6 and 12 are both equal to 0 mod 6. Okay, but even though that statement is true, 2 is not equal to 4. So a way of looking at this is that we can't cancel the 3's, okay, because 2 and 4 are not the same elements in this ring. Okay, so the cancellation property fails in Z6 for this example. Okay, let me give you one more example. Okay, in the ring Z10, we have 5 times 1 equals 5 times 3. Okay, do you see why that's true? Because 5 and 15 are both equal to 5 mod 10, so the result of those two calculations is the same in Z10, but we can't cancel the 5's. 1 and 3 are not the same element. Okay, so that's kind of peculiar, isn't it? Okay, this very natural cancellation property that we're so used to using in the real numbers just doesn't work in these two rings. Okay, so we could ask the question, what's wrong with these rings? Why doesn't the cancellation property work? Okay, well, looking up at the first example, you might notice just kind of a little weirdity that's going on in the ring. It's kind of strange that we can take two non-zero numbers like 2 and 3 and get 0, or 3 times 4 and get 0. Okay, and then down below, the ring Z10 also has that behavior if we pursue this a little bit farther. So I'm going to take the calculation that we did in Z10 and just take it a couple more steps. Okay, observe that if we start with the calculation that we did and just subtract the 5 times 1 from both sides, we can rewrite that as 5 times 3 minus 1 equals 0. There we're using the distributive property that holds in any ring. And notice what that leads us to. That tells us that 5 times 2 equals 0. In Z10, there's that strange behavior again of taking two non-zero numbers, 5 and 2, and multiplying them together to get 0. Okay, and so as a result of this behavior that we're seeing in these two rings, we're going to make a definition. Okay, let's step down to this. Okay, so we'll start with a commutative ring. And then let's read this together and fill it in. Then a non-zero element A and R is called a zero divisor. That's our new term. If there is another non-zero element B such that AB equals 0. Okay, this is kind of a strange definition, so let me rephrase it and then we'll look at some examples here. Okay, so a zero divisor is, or let me say it this way, A and B are zero divisors in a ring if they're non-zero elements that you can multiply together to get 0. Okay, so just to give you an example based on what we did above, in the ring Z6, 2 and 3 are zero divisors. Okay, why is that? Well, they're zero divisors because two things are true. We can multiply them together and get 0, and the numbers themselves are non-zero. Okay, so 2 times 3 equals 0, but 2 is not equal to 0, and 3 is not equal to 0. Oh, and actually, I should mention the ring here, so let's back up here. I'm going to try to write a little bit smaller. Okay, so 2 and 3 are zero divisors in Z6. We need to be specific about the ring. Okay, and the reason for that is that we multiply them together and get 0, but the elements themselves are not 0. Okay, so again, to be a zero divisor, an element needs to be non-zero, and it needs to be possible to multiply it by something else that's non-zero to get 0. Okay, can you find me some zero divisors in Z10? How about 4 and 5? Okay, those are zero divisors in Z10. Okay, and the reason there is that 4 and 5 are non-zero numbers that we can multiply together and get 0. Okay, and then with that definition, we are ready to define integral domain. That's this new definition that we mentioned at the very beginning of this video. Okay, and we're ready to write down what that is. So, an integral domain is a commutative ring with unity and no zero divisors. Okay, so kind of the thinking behind making this definition is to say that having zero divisors is strange, kind of. Okay, it seems weird that we can take two non-zero numbers, multiply them together and get 0, and so we're just going to say, all right, let's assume we don't have any zero divisors, and a ring where that's the case, where we don't have any zero divisors, is going to be called an integral domain. Okay, and as we'll see, as we proceed further into this chapter, integral domains have a number of nice properties. They behave more consistently with the way that we're used to having numbers behave.